Another gas law in topic 3 is known as Gay-Lussac's law. Gay-Lussac's law deals with pressure and temperature. At constant volume, the pressure of a gas increases with increasing temperature. So if you heat up a gas, the pressure of that gas will also increase. Gas pressure, if you remember, is the result of collisions of molecules with the container walls. So if you heat up a gas, increase the temperature, you have more collisions, therefore more pressure. The energy and frequency of collisions depend on the average kinetic energy of the molecules. And because the Kelvin temperature depends directly on average kinetic energy, pressure is directly proportional to Kelvin temperature. So it's a direct proportional relationship between pressure and Kelvin temperature. Gay-Lussac's law states that the pressure of a fixed mass of a gas at constant volume varies directly with the Kelvin temperature. And if you look at the shape of the graph of pressure versus temperature, you notice that it's a straight line. So if the temperature goes up by 100 degrees Kelvin, the pressure goes up by 1. And so then if it goes up to 200, the pressure changes to 2. So it's a direct proportional relationship. Gay-Lussac's law was named after a scientist named as Joseph Gay-Lussac, who discovered it in 1802. Mathematically, Gay-Lussac's law can be expressed as pressure equals K times temperature, or pressure divided by temperature gives you a constant. So you want to remember that taking pressure divided by temperature gives you the constant. P stands for pressure, T is Kelvin temperature. So most likely the temperature will be given to you in Celsius, so you have to remember to add 273 before you plug it into this relationship. This equation reflects the fact that pressure and temperature are directly proportional to each other at a constant volume. So the gas law that you want to remember is pressure 1 divided by temperature 1 equals pressure 2 divided by temperature 2. So the mathematical operation you'll have to use quite often with this gas law is cross multiplying. So you'll have to take pressure 1 times temperature 2 and divide it by temperature 1 to get pressure 2 or something like that. P1 and T1 represent initial conditions, and P2 and T2 represent a second set of conditions. So you'll most likely be given 3 of the 4 variables, and then you plug those numbers into this equation and then solve for the 4th variable. So you can either plug them in and then use algebra to solve for it, or use the formula itself to solve for the unknown, then plug the numbers in. Whichever way you feel more comfortable doing. So let's look at an example problem. You have a gas in a container at a pressure of 3.00 atmospheres. Keep in mind sig figs will be important at 25 degrees Celsius. Notice the temperature is given in Celsius, so you'll have to add 273 before you plug it into the equation. Directions on the container warn the user not to keep it in a place where the temperature exceeds 52 degrees Celsius. This might be something like an aerosol can. So if you ever look on the directions of an aerosol can, it says keep away from heat or fire, or not to exceed a certain temperature, because as that temperature of the gas inside that canister goes up, the pressure will go up. What would the gas pressure in the container be at 52 degrees Celsius? So here's the solution. We have the initial pressure is at 3 atmospheres. The initial temperature is 25 Celsius. Remember to add 273 to get 298 K. Then you plug the 298. Notice you have 3 sig figs for 298. So keep that in mind. Don't go with 2 sig figs from the Celsius temperature, but go with 3 sig figs from the Kelvin temperature, because that's the number you actually plug into the equation. So if we rearrange the formula P1 over T1 is equal to P2 over T2, you get P2 equals P1 times T2 divided by T1. So notice that we cross multiply. That's the key mathematical operation for this. So plugging those numbers in, we have 3.00 times 325 divided by 298, and you get 3.27 atmospheres. Another sample problem. Again, you can always pause the video to try to solve the problem yourself before the solution is presented to you. The gas in a container is at a pressure of 6.00 atmospheres at 35 degrees Celsius. What would the gas temperature in Kelvin in the container be to cause the pressure to change to 8.55 atmospheres? So if you start off with your formula P1 over T1 is equal to P2 over T2 and plug the numbers in, or solve the formula for the unknown, which will be T2, then you have to remember that that temperature is in Kelvin. So that will be your final answer. So plugging in the second pressure times the first temperature, remember we cross multiply, and then divide by the 6.00 atmospheres, we get 439 K. The initial temperature was given to you in Celsius, but notice that the problem wanted it in Kelvin, so we can just leave it as 439 K. If they wanted it in degrees Celsius, then you just have to subtract 273 to get your answer in Celsius. So if you'd like to work out some additional problems, turn to page R99 in the back of your textbook, and problems 245 through 247 are located there. You can try those on a separate sheet of paper or your note sheet. You should have plenty of room left on your outline page to do these example problems, and the following slides will have your answers. So you can always pause it at any time to check your answer. See your teacher if you have a question or as why an answer is the way it is. So if you remember letters D and E, you have to subtract the 273 from the answer you get from the formula to get the desired degrees Celsius. And it doesn't matter what the pressure label is, could be atmospheres, could be kilopascals, as long as it's the same pressure label for both initial and final.